in this video, I'm gonna talk about not just regression and classification with a single tree, but with multiple trees, which is known as ensemble learning. Okay, and random forest is one special case. Random forest is a special case. So decision trees are fast, simple, and interpretable, and very easy to explain. But it's invariant under the scaling transformation. So single tree, decision tree. Are fast, simple to calculate, and it's interpretable, easy to explain, and it's robust to irrelevant features. Because irrelevant feature will not be selected in our decision trees. So only the important variable will be used for splittings. But they are not best at prediction. Single tree, regression tree. It's not best for prediction. Compared with the classification or regression methods we talked before, even the linear regression, multiple linear regression, and also it has high variance. So compared with methods we learned before. And also the single tree has high variance. So in other words, even with the same data set, we apply the algorithm, we might get different trees. Even the same, this model usually give single tree usually give the high variance modeling variance. For example, suppose we take a training data set, split it into two halves, and train two decision trees, one of each of the half data. It's not uncommon for the two trees, it turn out to be very different, which is not unexpected, right? So in particular, if the two trees pick different features for the very first split at the root trees, then it's quite common for the tree to be completely different. So the decision tree tend to have the very high variance. So think about how do we fix this? So similar, which means high variance means similar data could give very different trees. So think about how to fix this. So how to fix? How to fix this? So there is one example. For example, if we know our data, okay, if we have some normal distribution with average 5, standard deviation 4, okay, we simulate some data. So for the first time we simulate data, probably we get 5, 6, 8, 9, and 1, 0, okay. And for another, so when we simulate another data, okay, we can calculate the average here, right? Mu1 here, the x1 bar. And we can, for another even we know the true model is this one, but when we simulate another data, for example, we could get different numbers, 8, 6, 5, 2, 2, 1, okay? We can get x2 bar. So these two numbers will be very different, right? But we wanted to know this true 5, right? But if this is different, what should we do? Okay. If you just generate one number, it has a high variance, right? But if you want to generate n random numbers, take the average, then the variance is n times smaller. For example, if you only have the 10 data points, you get a variance. If you get simulate 100 data points and then take average, your variance will be much smaller. So, motivated by this, we can reduce the variance of decision trees by taking the average answer of the branch of decision trees. Okay, so we could reduce the variance of decision trees by taking average of a branch of these decision trees. Average of a branch of decision trees. So that's the idea of the ensembling learning methods. Actually, this idea is also called the wisdoms of the cross. Okay. So wisdom of the crowd is there is a famous story that in a 1900s there is England there is a contest to guess the weight of the ox. Okay, a scientist named Galton was there, and he did an experiment. He calculated the median of everyone's guess. Okay, the median guess was the median guess from a poll survey of 1,000 gives you the 1,207 pounds. Okay, and the true value of that cow is 1,198 pounds. So the error is less than 1%. So even the the ox expert present didn't estimate that accurate. So this is called the wisdom of the crowd. The main idea is that sometimes the average opinion of a bunch of the idiots is better than the opinion of the one expert. And so it is with the learning algorithms. So we call a learning algorithm each person, even he does not know the call weight a lot, we call each person's opinion is called a weak learner. Weak learner. Okay, if it does better than guessing the randomly, and we combine the bunch of the weak learners to get a strong one, and the turn out to be giving a good performance, good guess. Okay, so what we can do is we can take the average of the output from first, we could apply different learning algorithms. Different learning algorithms. For example, for the classification, we can apply the logistic regression. We can apply the Gaussian discriminant analysis. We can also apply the classification trees. Second, we can average the same learning algorithm but on different training sets. Actually, the random forest is this case. We apply the same random forest but on many training sets. Third one is called bagging. So bagging means same learning algorithm on many random samples of the one training data set. So yeah, in most reality, we don't have many different training data sets, right? We have only one training data set, but how can we get many results from one training data set? Is we can get the same learning algorithm on many random subsample. Of one training set. And the last case will be close related to the bagging, is called random forest. Maybe I will just call it random forest here, random forest. Randomized decision trees on random samples. Decision trees. on random subsamples. On random subsamples. So the bagging and random forest are the most common ways to use averaging because usually we don't have enough training data sets to use fresh data for every learner. Meta learner takes test point, feed it into all different learners, return to the majority of the average output. And averaging is not specific to decision trees. It can work with many different learning algorithms, but it works particularly well with the decision trees to improve the prediction accuracy. Regression algorithm take the median or the mean output, okay, for the regression trees. Regression algorithm. Algorithms. We can take the median or mean output of several of all weak learners. And for the classification, algorithm, okay, we just take the majority vote. Or average the posterior probabilities. Okay, maybe I will show you one example. I'll show you one animation with simple learners. So you can see here. So we keep training. We keep training the decision tree with one depth. Okay. Let's see again. So although each step shows you the clear single, but if you take the average, it sort of give this contour plot looks like regions for different classifications. So this is a tree with depth 1. So if we have the tree with depth 2, if we take the average of the 100 trees, so this is on the right hand side, that's the results. Let's see one more time. We can see how if we take the average, the boundaries get blurred and we get more soft decision boundaries. And actually, this bagging method works in real life too. In the Netflix prize was on open competition for the best collaborative filtering algorithm to predict users' rating for films based on the previous ratings. It runs for 3 years and ended in the year 2009. The winners used an extreme ensemble method that take the average of the many different learning algorithms. In fact, a couple of the top teams combined into one team, so they could combine their methods. Then they say, let's average the model the model results we have and split the money. And this is how they win that data science competition. So combine different learners will give us different a combined model with low bias, okay? Because the decision tree gives low bias, right? So the combined bagging of learners combined results with low bias. For example, we can grow each tree relatively deep. Okay. Combine results from the low bias learners. Combine results with learners with lower bias. I would say combine the results from learners with low bias and high variance. So each tree, if you combine each tree may have the high variance, but combined trees will reduce the variance. Reduces the variance. So it solves so we will have some results with the lower bias, and at the same time we have the lower variance, which is a better case. So each learner may be overfit, but each overfit in its own way, and averaging will reduce the bias. And so that we could also get a nonlinear decision boundary from the linear classifiers. So, for example, we could get nonlinear decision boundary from linear classifier. So this is also another way to get the nonlinear decision boundaries. So for example, let me show you one more example. Yeah, for example, this case. So on the left hand side, we train this classifications using the linear decision boundaries. Okay, but if we take the average of the linear decision boundaries, as we can see, we take the average, we will get sort of nonlinear decision boundaries. You can get this contour shaped, ellipse shaped contour plot. Actually, this bagging, so what's this bagging mean? Bagging actually stands for bootstrap. Aggregating. Sorry. Okay, this is a methodology is proposed by a professor named Leo Bremen. In the year his paper is published in 1994. Okay, is by a statistician. He's a statistician. He also involved in introducing the random forest. Also the co-inventor. Random forest. So bagging is a randomized method for creating many different learners from the same data set. It works well with different learning algorithms. One exception seems to be the k-nearest neighborhood. Bagging mildly degrades it. So what's the idea? What's the idea of this bagging? So in general, how this bagging is generated. So suppose you have given a n sample data point. Training sample. Okay, generate a random sample. So because it's called bootstrapping, which means you generate a sample based on the sample of size n prime by replacing random shuffling with replacement. With replacement. With replacement means points can be sampled multiple times. Can be sampled multiple times. Okay. For example, if we have the n, if we choose n just equal to the n prime, so we want to subsample the same sample size as the original sample. Okay. Actually, around 63.2% of the original sample sampled. Okay. And then based on this random sample, build the learner based on sample n prime sampled random sample. And repeat until we get T learners. Okay, this T learners we could use the decision trees. We could use support vector machine. We could use a regression. Okay. So if the same point sampled multiple times, which means in each of the learner will have more weights. So yes, so that's the basic idea of the bagging algorithm. And in the next video, I will show you a special case, step forward, one step forward of back-in, and which is one of the most famous machine learning algorithm. It's called a random forest.